Okay, I think I've called the people.
It's because it was muted.
Jak tam Ewa Pajor inspiruje córkę, czy...
No wiesz, jak ona ogląda te mecze F1 kobiet, to tak się irytuje. Nie, pan lubi.
Ja mam pierwszy dostałem w domu i umówił się przerodował z pewnością. I nie widziałem, czy już mam dzwonić.
Widziała wszystko, tak? To będziemy lecieli. Okay. So I think we can start. Everything seems to work amazingly. We'll see how it goes. Okay, so today we are having a very, I would say, ambitious, ambitious topic. So Max Locke from Vienna will tell us, finally we'll understand where does irreversibility in quantum theory come from.
Thank you very much. So just to clarify, the question is ambitious, the answers are more modest as you would expect, in the fact that I don't have a Nobel Prize. So yes, thank you very much for being here, and thank you to everybody for coming. Yes, as my title suggests, I'd like to talk about the emergence of irreversibility in quantum mechanics. The talk will be split into two parts, although really it'll mostly be the first part, and then the second part will be an application of the first part. I've tried to perhaps try to pack in more things than there is time for. 45 minutes, so actually including questions? Or...
No, 45
okay,
plus
perfect.
But we will interrupt you.
Okay, sure. Good, yes, so, okay, let's get started. So, part one, second law of thermodynamics and isolated quantum systems. So, I'd like to maybe motivate this with a quote that I very much like, from Arthur Eddington in The Nature of the Physical World. He says, if someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Right? So in other words, if I stand here and I say, I have a new theory, and there's a small violation of Einstein's equivalence principle, you'll probably think I'm wrong, but you'll listen. You'll think maybe he's doing some science. However, if I say, in this talk, I'm going to propose to you a perpetual motion machine, no one will take me seriously. You'll all think I'm a crackpot. And rightly so. But why rightly so? Why do we have so much faith in the second law of thermodynamics compared to all other laws? In fact, if I can abuse my position as speaker for a moment, I'd like people to put their hands up if they really believe that they can give me a general formulation of the second law, applicable to all circumstances, as long as there are enough degrees of freedom. Will anyone put their hands up? Be brave enough that they could say this thing? Yeah, so we're in this very strange situation, right, where we have this law that we're absolutely sure is correct, yet none of us are really confident enough to state it. I find that kind of paradoxical and kind of exciting, right? Okay, so a little bit of history then. When we asked this question, what is the second law of thermodynamics? The first formulation of it was by Thomson, also known as Lord Kelvin, that says that you can't purely convert heat into work. And then there are the later formulations by Clausius saying that heat can never pass from a colder body to a warmer body without some other change needing to happen at the same time. And then he later stated that this is really equivalent to the statement, the entropy of the universe tends to a maximum. And I think this is the formulation of the second law that most of us are the most familiar with, or that we see as the most general, is to say this idea that entropy somehow increases over time. So then, of course, the question arises, how do we get this apparent law from microscopic physics? And there's a little historical note. The book in which Clausius made this statement, in a later edition he removed this statement from the book because he was no longer sure of it. The one about entropy of the universe tending to a maximum, to be precise. Okay, so just a little technical point. It's very easy to confuse equilibration with thermalization. So when we say some kind of maximum entropy state, the first thing we have to do is explain how we reach this maximum entropy state. That's the process of equilibration. The second thing we have to do is to try to explain why that state has thermal properties, why that is the thermal state, why we can describe it with comparatively few parameters, such as temperature. So there are examples where, that we know of in the real world, where you can equilibrate to a system that doesn't have thermal properties. So many-body localization is a more topical example of this nowadays. So before looking at, or before asking the question of how the second law might arise in quantum systems, it's very instructive, I believe, to quickly run through the arguments of how people usually try to understand the emergence of the second law in classical systems. So the very first attempt at this, that I know of at least, was the H theorem by Boltzmann. He defined this function law of the distribution of energies, and then tried to prove, within the context of the kinetic theory of gases, that this quantity always decreases over time. But this wasn't some kind of second law, some kind of proof of irreversibility, because he famously made this assumption, the Stoßzahlensatz, which introduces irreversibility by hand. This is the assumption that individual scattering events are independent. Nowadays we might call this a Markovian assumption or a memoryless assumption. And this, of course, illustrates a general principle. We know from the Loschmidt paradox, as it's so called, which was a counter-argument to Boltzmann's H theorem, that an irreversible process can never really be deduced from a fully reversible process. On top of that, we have the Poincare recurrence theorem, which says with a certain asterisk, system will eventually return to a state arbitrarily close to its initial state. Of course, if I think about a commutative universe with two particles flying off in two different directions, then of course there will be no recurrence in this universe, but when we're thinking about thermodynamics, we're thinking about substances and some kind of closed, some kind of box on the table in front of us, something like this. And in that context, the Poincare recurrence theorem doesn't apply. The kind of initial attempts to try to understand this might say, okay, well, the problem is that we start by not really knowing the system, and somehow the second law of thermodynamics will come from our initial ignorance of this, right? So Gibbs famously quantified the entropy of the system by this famous formula, which nowadays we might more likely understand as the Shannon entropy, where you take the probabilities of being in various states, sum over them, this quantifies your ignorance somehow, and then perhaps this is the quantity that will determine how irreversibility emerges. But of course, initial ignorance isn't enough. Neuville's theorem tells us that the distribution in the classical phase space acts like an incompressible fluid. And what that means is that the Gibbs entropy is constant. And so, in fact, all classical derivations of the second law require two things. They require some kind of assumption of a low entropy initial state, sometimes called the past hypothesis, particularly in the context of cosmology. And then second, they require some mechanism by which information can be lost, or some notion of coarse graining. So, a common illustration of this, and I think perhaps the most usual understanding of the emergence of the second law, is the following. You take some kind of cell in phase space, you watch it evolve in a system which has the appropriate properties that will somehow mix up the phase space, and then you watch over time, as you see in the top, the distribution spreads itself around phase space, such that if I can't really resolve an individual point, but rather I'm restricted to some kind of cell size, because this thing is so thoroughly covering the phase space, that cell size will give me an effective increase in my ignorance over time. I think this is not a great argument for the emergence of the second law, and in part because it doesn't really capture all circumstances, right? If we now instead consider an ideal gaseous box and look at the distribution of speeds, we know that from century of work, that this distribution of speeds will tend to the Maxwell-Boltzmann distribution. That's the equilibrium state, so to speak, of this system. So if we consider now some out of equilibrium distribution of this, simulate a box full of a classical ideal gas. This corresponds to a point in phase space, an incredibly high-dimensional phase space, of course, but nonetheless it's a point in phase space. And then, if we run the simulation, we see, of course, as expected over time, the distribution of speeds tends towards the Maxwell-Boltzmann distribution, this orange curve here. But crucially, it's not equal to the Maxwell-Boltzmann distribution. Of course, it continues evolving. There continues to be a single point in phase space evolving reversibly, and that's what accounts for the fluctuations that you see against this sort of background of this orange curve. And of course, we expect these fluctuations to decrease with the size of the system. So what's happening here? I mean, this is not some kind of cell in phase space, some initial ignorance spreading around, and then some kind of cell size in phase space. The whole argument doesn't make sense here. What's happening instead is that we're not really talking about the system. We're talking about an observable in the system. This graph at the bottom does not characterize the system. It characterizes this one specific observable for which there is a highly many-to-one relationship between points in the phase space and values of the observable. And that's the really crucial thing, and that's the thing that will continue to hold when we think about the second law in quantum systems. So I set this challenge at the beginning of stating the second law of thermodynamics. So the best version that I can think of, at least, of this statement would be that a certain set of observables, that is to say the coarse-grained ones, will approach and mostly stay close to the distribution associated with the state maximizing the Gibbs entropy on the phase space. Kind of a handful, but I think it more or less encapsulates the most general statement of the law. Of course, there are assumptions that go into this. You need the system to explore enough of the phase space, for example, by some kind of ergodicity argument. But the sort of broad point coming from this is that the second law is kind of a loose collection of statements which one can formalize in different ways in different contexts. There isn't really one second law, as much as I've tried to find the most general version I can. Sorry. So that was classical. Let's move to the quantum. So if we naively take this Clausius statement that the entropy of the universe tends to the maximum, and try to apply this in an isolated quantum system, of course, the immediate question is which entropy? So the usual quantity taken to be the thermodynamic entropy in a quantum system is the von Neumann entropy of the density matrix. But of course, we immediately run into a problem, which is that the von Neumann entropy is invariant under unitary evolution. An isolated system evolves according to some time-independent Hamiltonian, which generates some unitary evolution, which of course then means that the von Neumann entropy is constant. Well, you might be then tempted to say, okay, well actually an isolated quantum system shouldn't equilibrate. It's only an open system which equilibrates. I mean, first of all, there's then the question, most people would understand an open quantum system as embedded in some larger space where there is another quantum system interacting with that quantum system, and so you haven't really solved the problem then. And secondly, and probably more importantly actually, it's simply not borne out by the evidence. So there are many examples of very nice cold atom experiments where you see the equilibration of observables despite the effectively isolated nature of the system. Unfortunately, that doesn't get through to everybody, and so sometimes you get annoying remarks by referees. But anyway, we can deal with those. So just to sort of jump straight to the end, or to the kind of key point about how a quantum system can equilibrate, the picture is the following, which I will make now more precise and more mathematical. What you have is the system evolving, the system state, denoted by rho here, evolving with time on some kind of unitary orbit in some incredibly high-dimensional Hilbert space. And then what you have is some reference state, if you like, which we'll call the equilibrium state for reasons which you can probably guess, according to which most, a certain class of observables, let's say, which I will also make precise, will see the equilibrium state rather than the actual evolving state in time. That is to say, if I have an observable which can discriminate every state in the Hilbert space, then of course the appropriate description for this observable, the appropriate state to use for this observable, is the actual state of the system evolving with time. However, the observables for which there is a many-to-one relationship, just like the distribution of speeds in the classical case, those will, after a certain equilibration time and with many caveats which we'll come to, see not the state evolving rho of t, but in fact the equilibrium state, rho of equilibrium, which can in general be very different from the actual state evolving in time. Yes. So the picture we have here is actually a kind of a dynamical typicality in the phase space, if you like, the quantum phase space. That is to say, from this picture, equilibration is not really the arrow of time. I mean, we can discuss this in more detail later if you like, but rather it's an accident of the past hypothesis. We've chosen a state for which observables which do equilibrate, that is to say, observables for which this rho ec is for most times a good description, and you happen to have chosen a point along the path where that doesn't hold, but as the system evolves very quickly, because of this principle of dynamical typicality, that observable will instead see the equilibrium state. It's simply an accident of the state you chose, rather than any sort of fundamental arrow of time.
But you will still have some recurrence time.
Yes, of course. Yes, absolutely. I said many caveats. That'll be wonderful. Okay, so how do you get this equilibrium state? So there are a couple of ways to calculate it. This is perhaps the most intuitive, or the easiest one to write down. That is to say, you simply take the evolution of the state across this orbit and average it across that whole orbit. So people who are familiar with quantum reference frames or symmetrization or these kinds of things would understand this as averaging over the symmetry group, that is time translations, such that the state becomes symmetric with respect to that group. But it's important not to understand this necessarily as a physical statement that I'm going to only talk about observables which are somehow averaged over time, right? This is a calculational trick, if you like. It shouldn't be taken physically too seriously. And so then how can I justify calling this the equilibrium state? Well, there are some nice results, as you can see here, for example, showing that if I mean, this might look complicated at first glance, but we can unpack it. Take the expectation of value of some observable with respect to the actual state, some actual moment in time. Take the difference of that with the expectation value associated with the equilibrium state. You can find that along the trajectory, this is on average bounded above by a quantity which is the difference between the highest and lowest eigenvalues of that observable divided by the effective dimension, a quantity which I'll define it more precisely. But broadly speaking, the effective dimension is the dimensionality of the space explored by the evolution. So if I begin in an energy eigenvalue, my effective dimension is 1, because I've simply evolved according to a phase. This is a one-dimensional space. But if I begin in a superposition of many different energy eigenvalues, then my effective dimension is much higher. Another way to understand this is that if I take this state evolving along the trajectory, as I described before, if you imagine taking all of these individual states along that, putting them into a bag, I rummage around inside the bag and I pull out at random a state at a given moment in time, and I compare that to the equilibrium state, what's the probability that the expectation value of the observable will be greater than some amount? And you find that
this variance on the right is for equilibrium state. This
variance.
I mean, on the top.
Oh, this thing here.
Yeah.
That's the difference between the highest and the lowest energy eigenvalue.
Ah, okay.
It's a property of the observable.
Okay. So
what this thing does, precisely that, is compares the range of values of the observable with the effective dimensionality of the space explored. So when the effective dimension is very large, in particular compared with the range of values of the observable, then the probability that you get something that's significantly different from the equilibrium state along the trajectory is very low.
What is so? I mean, I'm familiar with this from an extent, but what is so special about quantum systems? Why one cannot can one apply similar methodology for pure classical systems?
I believe so. I unfortunately haven't found anyone doing it, and I would really love to see a side-by-side. Somebody having done that, and then a side-by-side comparison, or someone worth to do that. I have fantasies of doing it myself, but unfortunately, I haven't really done classical mechanics since a very long time. So I don't trust myself to do it well. But I mean, if you know someone who's very good at classical mechanics, then send them my way, because I would be very interested. Classical statistical mechanics. Yes. Okay, so these are statements about the averages of observables. It's very cool, very, very cool. When I first saw this stuff, I was very surprised. But it's still fairly limited. One can apply this to subsystems of a larger system evolving in a magnetic fashion and show that the average distance of your reduced state from the trace over the environment, let's say, the system you don't care about, of the equilibrium state is bounded above by this quantity, which is the dimensionality of your small system squared divided by the effective dimension. So then we move from averages of observables to actually a statement about states, which is of course very interesting. And then finally now an actual definition of the effective dimension. It's related to, sorry, did I? I did, yes. So these pi's here inside the traces are the projectors onto the spectrum of the Hamiltonian generating the evolution. So let's look at an example of this. We take the quantum Ising model, that is to say, a bunch of spin halves in a chain with some free term and then some interaction term.
Yes, so you can answer at the end because I don't want to destroy your thing, but there were these results that you heard me how in the back of Gogolin and ICER.
Yes.
And then I think they showed there was this equilibration in time of concentration of measures happens even for trace norms.
Trace norms.
So some kind of, it's not really observables, it's really distances between states.
Mm-hmm.
So I don't remember these papers, but I mean,
So for subsystems, yes, this happens.
but this was...
For the overall system, you can't have an observable independent norm happen. It's impossible. Unless it's just
for a closed system, if I average
exactly because you can always pick some observable which can distinguish, which can tell you that the system is involved. Right? If I pick, for example, if I construct a POVM by taking an equal weight of all energy eigenvalues and giving them a phase that evolves in the usual way, e to the I omega t. If I make a state like that, make a projector of those states, those in general don't form a projection value measure for various reasons. I can go into the end if you like. But they do form, they are positive and they sum to the identity, the appropriate normalization, so they form a POVM. And that observable is a covariant time observable. It's one that's specifically constructed such that the Hamiltonian will maximally generate evolution in that. And that will never, that by design, has to continue evolving in a regular fashion. I can't equilibrate those observables. That's a time observable.
And when you say equilibrate, you mean it will never spend the most of the time in the equilibrium.
Exactly.
Thank you.
So yes, so let's look at an example of this. We take the Ising model, which I hope most people are familiar with, at least by name, and look at the normalized bulk magnetization, which of course is a many to one observable. It says effectively how many of the spins are pointing up or down. And then we start in, of course, a very low entropy state, so to speak, which is that all the spins are pointing down. So, I mean, as you can see, if we take simply 5 spin-half particles, then actually already you see some kind of something you might like to call equilibration-like behavior, in the sense that you jump far away from the initial value and then stay close to your sort of equilibrium value, if you like. But of course, the fluctuations are very, very large, right? And they're on the scale of the kind of evolution, the initial evolution. So it's not really fair to call this equilibration. Then if we take 9 spins instead, you see actually already you see something very close to an equilibration-like behavior. The dotted lines give you the equilibrium values as calculated by the previous formula. So that is to say, the values associated with the equilibrium state. And you can see you kind of stay mostly around the equilibrium value, but with very large fluctuations. And then with 13 spins, this blue line here, you can see that you fluctuate for quite a while, but then as time goes on, you get really quite close to this equilibrium value, and you stay really quite close to it. So this is equilibration on average in action. These are not, when I say equilibration on average, I don't mean these are average values. This is the actual, taking the actual state at an actual moment in time and calculating the expectation value of the observable. So from this, you often hear in lectures that the thermodynamic limit is n goes to infinity. in this model, the thermodynamic limit looks like n goes to 14 or 15. So that very much surprised me. It's a much much faster convergence to your equilibrium behavior than I would have expected. So, I mean, why should we expect an isolated system to increase in entropy? Well, as we see, it equilibrates, appears to show irreversible behavior. Right? So I think I've been through most of this already, but just to really hammer it home, the state does not evolve to the equilibrium state. It becomes, on average, close to it with respect to averages of some observables or with respect to some subsystems. The evolution is still unitary. And of course, becomes close to it. There must be some, if you start in some out of equilibrium state, there must be some equilibration time. This is a very interesting topic, a very difficult topic. Everything something I snuck under the rug before was the inclusion of degeneracies, and in particular degeneracies of the gaps between energies, makes this a little bit more complicated. Still works totally fine, the formula just got a little bit more complicated. There are, of course, recurrences, but I mean, the familiar argument against the observational Poincare recurrences is that they very quickly, when you calculate the recurrence time, it very quickly becomes larger than the lifetime of the universe. And of course, the same is true with the quantum Poincare recurrence theory.
So in this case, what would you call the entropy?
We'll come to that.
Okay.
And of course, something I really haven't touched upon at all is that you need a large effective dimension. And arguing that the effective dimension is large is a non-trivial thing, and that's a large part of the work that Christian and Jens Golden and Isaac did. Okay. So the rest of this section, at least, how much time do I have? Okay, good. The rest of the section will be dedicated to this question. And so, if the equilibration only really happens with respect to observables, then it's reasonable to investigate the idea that perhaps the entropy should also be defined with respect to observables, i.e. the observables which equilibrate. So, some ways to get observable derived entropies are, well, very simply, you can take the observable, calculate the probability distribution associated with it, and then calculate the Shannon entropy of that probability distribution. Yes, and of course this looks precisely like the Gibbs score in that way. Another approach, which is quite popular and was actually part of my motivation for beginning to study this, was the goal to understand this quantity, is the so-called observational entropy. This was originally introduced in a very particular context by John von Neumann in the 30s, but then largely forgotten and then revived in the last 20 years or so. So you can see this looks a lot like the Shannon entropy, but it has this VI term, which in the case of a projective value measure is just the rank of the projectors, the rank of the projector associated with that outcome. So what does this do? You can see, if you think about what this, you can do it better. If we take this log term, sorry, if we take this log term and use the rule that the log of the ratio is the difference between the two, there's a minus sign here, so what does this do? It gives you some positive term that you add onto this that scales with the logarithm of the size of the subspaces you're projecting onto, if you like. So,
Max, so can I look at it as a relative entropy between the Shannon one and the microcanonical?
That was my first thought too, and there is a way to try to understand it like that, although...
Formally it looks like that.
So this would be, the problem I had with that, maybe you can help me with this, is that this should also be a probability distribution, right? It should also sum to 1, and this doesn't sum to 1, it sums to the dimensionality of the space.
But you can renormalize.
Right, right, exactly. So then one could define observational entropy version 2, observational entropy version 2, appropriately rescaled like that. And that was, I mean, von Neumann's original argument for introducing it was to try to get a relationship with the microcanonical entropy. But I mean, that research program kind of ended before it really started. And then in the more modern version, people don't include the dimensionality.
And do you know what was their motivation? Did they want to see what is the difference between the two entropies? Because that was a big question, right? What is the difference between the Shannon Gibbs and the microcanonical entropy?
So, no, strangely, and that's again, was a large part of the motivation for me starting this in the first place was seeing this work saying the observational entropy is the appropriate thermodynamic entropy in a quantum mechanical context, and asking the question why. What's different between that and the Shannon entropy? And we'll find out the answer is not a whole lot. So, but don't all go home just yet. Okay, so I should probably speed up a little. So that's the observational entropy. So if we want to talk about the use of these things to quantify the equilibration of quantum system, using the previous work, we have a problem, right? Because what I showed you was about the equilibration of subsystems, or it was about the equilibration of averages of observables. So the first thing we have to do is to take that work and then generalize it to not just the equilibration of the average of some observable, but to actually show that the whole observable equilibrates, all of its moments, in fact, its probability distribution. And that's precisely what we did. So if you take the one norm, the difference between the probability distribution, so I'm sorry, I've switched notation now. Omega is rho, the omega is the equilibrium state. If you take the difference between the probability distribution associated with that observable at a given moment in time, take the difference between that and the probability distribution associated with the equilibrium state, take the norm of that, and then average it over time, you'll find that it's bounded above by this quantity. So what is this quantity? R is the number of distinct measurement outcomes, this is the effective dimension as I described before, and this quantity here, this really just accounts for the finite equilibration time and the possibility of degeneracy. So as the time goes off to infinity, this part becomes zero, and this whole quantity just becomes the number of energy gaps in some interval epsilon. So this is really a family of bounds, effectively. You can see this as I'm scaling this epsilon, this n will get larger and smaller. There'll be some minimum number of this, which will give me in the long time the best bound. But that tends to be a small value of this, which will mean that the characterization of the bound of the short-term behavior is not very good. But if you want to simply compare it with the thing I showed you before, you can take t to infinity and then pick the minimum of this value, and then there you go. That's the best bound. Okay. Yes. So actually, this kind of we can kind of close it here, right? Because what this means is that any entropy, any continuous entropy that's defined with respect to the probability distribution will tend to a fixed value. So you don't need the observational entropy to show you that the system will equilibrate. The Shannon entropy will also reach some fixed value. And then to really clarify the physical content of this, note that this difference between the probabilities really is characterized by this ratio: the number of outcomes, the number of distinct measurement outcomes, which we can kind of understand as macro states. If this observable is something like the bulk magnetization, which we can see on a macroscopic level, the ratio of that quantity with the number of orthogonal states explored through the evolution, which we can kind of see as in a dynamical sense the macro states. So this is really very nice. You can ask the question, does an observable equilibrate? And the answer is yes, if the number of states that it can distinguish is much smaller than the number of states the system will explore as it evolves.
So this is assumption, we assume here like a standard observable, like corresponding to projected measurement. Not POVMs.
There's a slightly modified version of this that holds for POVMs as well, which is in the appendix of this paper, but it holds this ratio remains the key factor. So yes, it holds for POVMs too, just not in this exact form. Yes, okay. So we can state a kind of second law for the Shannon entropy in the sense that the Shannon entropy will, of course, tend to its equilibrium, to the value associated with the equilibrium state, right? And likewise, we can flash through that very quickly, but I think it's very clear this is something that this quantity here was the sort of equilibration factor, if you like, and then this is the binary entropy. And so this for long times, this quantity here, sorry. Yeah, okay. So if we have a statement about the Shannon entropy tending towards a fixed value, it's not really a second law yet, right? I think everyone would agree. And just to make sure that we're really being clear here, it's not enough for the entropy to settle on some fixed value. Of course, we have to show that it doesn't fluctuate too much away from that, which is precisely what this result is about. And then likewise, we can prove the same thing for the observational entropy, effectively. That the difference between the observational entropy associated with the state and the observational entropy associated with the equilibrium state is on average small as the time increases. And likewise, we can prove that the fluctuation as well.
Sorry, can I ask, so do you, like, to have those concentration inequalities, do you use Markov inequality, just standard Markov, or you have some better understanding of fluctuations?
It's really, so this one is effectively, okay, so first, this one is based effectively on Fanes-Odenat inequality. You just prove you use the continuity of the entropy and the fact that the probability distributions converge. Probability distributions converge to each other. And since the probability distributions converge to each other and the entropy is continuous, then by Fanes-Odenat, you can show that the probability distributions converge to each other. And then for this one, you need to use the Chebyshev inequality.
Okay.
It's far simpler. It looks nice and fancy like this, but when you look at the proof, you see it's really very, very simple.
And Max, pardon, and can you try doing better than Chebyshev? So better than algebraic, and go to something like Levy concentration, where you have exponential bounds.
So there,
or it doesn't work.
That it shouldn't work.
It shouldn't?
Without extra assumptions.
It shouldn't.
Shouldn't work without, because so if these things are going to converge exponentially to each other, that's a far stronger statement than saying they will eventually converge to each other. For them to converge, I didn't say anything about integrability, non-integrability. I didn't say anything about chaos, anything about ergodicity. This is completely general. This is the number of. It's really just R divided by effective dimension, and that's enough. These things hold. If you want an exponential convergence, then you really need to make statements like you're going to explore the phase space thoroughly and quickly enough, with enough divergence from initial conditions, etc., etc. Those are the things that give you the exponentiality.
You have examples like what you have to add to your assumptions to get an exponential convergence?
No, this is an active ongoing work. This is something we would very much like to do. Because in fact, what you're asking about there is a characterization of the difference between, for example, integrable and non-integrable systems.
Yeah.
Right. And so this is the hope that we have, is that this formalism might give us a different way to understand that distinction. Because I mean, normal way you would understand that is in terms of constants of motion. So an integrable system is a system which has an extensive number of extensive conserved quantities. And there seems to be this sort of island in parameter space where if you take a Hamiltonian with some parameters, you'll have the situation where you're effectively integrable for some values of those parameters. And then as you shift them, there's maybe a very brief fuzzy region, but then very quickly you become non-integrable, and there's two completely different classes of behavior. As the systems get larger and larger, two completely different classes of behavior for those two cases. But there's kind of universality within those. So where does that universality come from? Why is that completely different behavior? I mean, none of those things are present in what anything that I've shown. So then it's really the very interesting and very exciting question: are they here but hidden, or is there something about the way we've asked this question which is completely blind to those things? And that's,
can you remind the definition of this effective dimension?
Sure. Where this is this is the projector from the spectral decomposition of the Hamiltonian.
Okay.
So you've zeroed in on exactly the right. I mean, this is our intuition as well, is that this will be captured somehow by the effective dimension.
Mm-hmm.
I mean, not only that, also this n quantity here. It's going to be the interplay between this and this in the end that characterizes this, but we're not. This is still very much speculative. Okay, I see I have 9 minutes left, and I haven't finished part 1, so maybe part 2 will be an advertisement for part 2, but there you go. Okay, so if we take the Clausius statement, even though Clausius himself actually disowned the statement, we can ask, when does the entropy of the universe tend to a maximum? Well, when is the equilibrium observable entropy maximum? Okay, when it starts in a low entropy state. Okay, that's a pretty, you kind of introduce this by definition, but fine. More surprisingly, the answer is actually kind of often. Of course, you can choose states in which this is not the case, but for most of the states which you would see as a sort of natural way to initialize the system, generally these tend to be low entropy states. There's a very interesting work exploring precisely this question of what the difference between the entropy associated with the equilibrium states and the entropy associated with the initial states. So, just to show you with an example, but I hope you believe me anyway, we return to this Ising model and now look at, say, the Shannon entropy associated with the bulk magnetization. We see that, in fact, yes, the not just the average value of the observable, but in fact the whole probability distribution, and therefore any continuous entropy associated with it, likewise shows this equilibrating behavior. So, a second law, versions of the second law hold on average, but as long as you make some quite fuzzy past hypothesis, I told you, you said it was an ambitious talk, of course, so the answer therefore must be partial. I mean, this is not at all satisfying. This is some sort of general principle in terms of the second law of thermodynamics. Finite fluctuations occur, decreasing the system size as expected, and you don't explicitly need to coarse grain the observable outcomes. It's enough to simply pick an observable which cannot resolve all of the underlying details of the space. So, as I said before, this is not really an entropy maximization condition. How does this
I mean, this is some kind of coarse graining. Why
It's not an explicit coarse graining. It's a coarse graining, a dynamical coarse graining. You don't have to do, for example, like the observational entropy does, and explicitly inflate the value of your entropy in order to account for coarse graining. But you're right, I mean, it is a coarse graining. The word explicit is the part that I really...
The number of outcomes should be small.
Yes,
This is this coarse graining.
Exactly. But you don't need to, for example, take observables and somehow integrate over outcomes. Okay, so in the remaining 6.5 minutes, I'm going to solve the measurement problem. So this is really an application of the first part, right? I showed you this picture before, which I'm sure everyone is familiar with, at least most people. We have this strange situation in quantum mechanics where you have this very fuzzy indeterminate world, and then suddenly, as soon as you make contact with some kind of classical measurement apparatus, these fuzzy indeterminate properties suddenly become determinate and objective and redundant and all of these things. And there are many problems associated with this. There's the version of the measurement problem that says, how is a particular measurement outcome chosen? I don't really find this question particularly interesting. I find it very hard to turn this question into something that can be a physically meaningful question. I like to discuss it, but I have a rule that I only discuss it outside of the lecture room and in a bar, preferably with a beer in hand. However, if we make a more precise question, there is a more precise question we can ask, which is how do we choose which physical situation should be modeled by, let's say, a unitary process, and which should be modeled by a measurement. One way of phrasing this is if I have an optical table and a beam, and I place an element in the path of the beam, what about the element that I placed there tells me whether I should see this as, say, a unitary transformation of the state or a projective measurement performed in the state. So if we're really asking what is a measurement, what is an observer, we're really seeking physical criteria on the physical systems that are performing the measurements, right? So if you think about some kind of qubit system, coupling to some kind of qubit system, we wouldn't ordinarily, if this is all there is, we wouldn't ordinarily call this a measurement, right? However, when you have somebody on the scale of Marcus Huber looking at your qubit, then this we would see as necessarily somehow a measurement. So what is it physically about Marcus Huber that makes him an observer that a qubit alone does not satisfy? Especially if we think that Marcus Huber might be himself composed of many qubits. And then there are, of course, some naive problems associated with simply taking textbook quantum mechanics and then throwing it at the situation. If I apply a projective measurement, I will break all three laws of thermodynamics. I don't think this will necessarily surprise anybody. Maybe you've not thought about it before, but if you haven't thought about it before, it'll take you a few seconds of thinking to realize the answer is that a measurement is an interaction, and therefore you're not really accounting for all of the thermodynamics in the situation. So let's account for all the thermodynamics in the situation. So in answering this question of what is an observer, what is a measurement, we have a set of desiderata. 1, no violation of thermodynamics. 2, observation is only induced by large systems in some sense. And 3, that the relevant information spreads out in a way that happens spontaneously, irreversibly, and doesn't require exact control of all of the constituents. If my photon detector if the construction of a photon detector required me to have exact control of every individual electron in the photon detector, I would be doomed never to be able to construct it. I mean, I obviously can't personally construct one, but you get the way. So, if we think about this process of equilibration that I just described, and look at this list of desiderata, we'll see that there's no violation of thermodynamics. It only occurs in large systems. It happens spontaneously. It's irreversible, with all of the caveats that we discussed, and it doesn't require the exact control of all the constituents. So let's turn this into a hypothesis that we can really test, right? So this is what we like to refer to rather grandiosely as the measurement equilibration hypothesis. This is the statement that the measurement process, or perhaps more precisely defined the quantum to classical transition, is an entropy increasing transition towards an equilibrium state. And this is not something that's actually new. This is something when you look through the literature, you will see hints of this idea and occasional explicit statements of it in throwaway comments, but no one ever really tried to formalize it properly. Okay, I don't have time for historical asides. Okay, so let's make a maybe more precise hypothesis. This is maybe a little bit more limited, maybe too limited, but that we can do something with just to play around with. So let's state it in the following way. Measurement is an entropy increasing transition from a system, potentially in a superposition, uncorrelated with its environment, to a region of state space commensurate with probes or observers or whatever you want to call them, finding a well-defined outcome for the system in an objective manner. That's a lot of words, but it can be summarized fairly easily in this picture. So if you consider a situation where you begin out of equilibrium, you have some system with some probability distribution associated with the outcomes in the measurement basis, and then some observers who don't know anything about that. And then if we allow the system to equilibrate, we can ask under what conditions does it equilibrate to a situation where the observers or the observer systems or the apparatuses or the environment fractions or whatever, according to your preferred interpretation, will all agree about the measurement outcome. So if we look at this kind of conditional form Hamiltonian, this is a purely phasing Hamiltonian, as Jarek very nicely informed me of. Excuse me. And then if we coarse grain the observers in this way, such that we have some sort of environment composed of many systems, many subsystems, and then we gather them together into sort of macro observers, if you like. And this is really there to try to encode this idea that I said before, that the spin of every electron in your photodetector shouldn't know the measurement outcome. That's far too much. It needs to be encoded in literally every degree of freedom. It should just be encoded somehow in the coarse macro degrees of freedom to which we actually, as macroscopic observers, have access to. So given that situation, the equilibrium state looks like this. We have the probabilities associated with the initial state of the system in the measurement basis, and then this tensor product of macro observers, and we find that the fidelity between different conditional states of macro observers decreases exponentially as we collect more and more systems into a macro observer. And so this in fact is it tends exponentially to this SPF state that maybe many of you are pretty familiar with, but which I didn't include a slide on. Sorry about that. And this coarse grain actually strangely seems to be necessary. If we take this Hamiltonian that I described before, and then select these Hamiltonians from some random ensemble, increasing the dimensionality is not enough to get the error associated with this. The error quantifies somehow the distance from this objective property. It seems to converge to this value as you just increase the dimensionality of a single observer system. You really need to have in this model at least, actually include more subsystems, and you get, of course, this exponential behavior that I described. So I'm 1 minute over time, but I'm basically done. So, in summary, at least at the second part, this measurement equilibration hypothesis gives this thermodynamically consistent picture of measurement, and it helps us to address this conceptual issue of when to model a process as a measurement, as an observer. It's when there's some kind of conditional interaction with enough systems such that this will spontaneously evolve to some equilibrium state, or with respect to the coarse grained observers. And then in the limit where we bunch together small systems into sort of macro observers, this can approximate the process of an ideal projective measurement. But this, of course, this was a very restrictive, very simple model. We could allow some kind of initial control, some kind of pre-measurement step in the Stern-Gerlach apparatus. You don't simply throw a spin at a wall and say, okay, equilibrate. what you do is you first of all carefully couple the spin degree of freedom to the position momentum degrees of freedom, and then let the system equilibrate. So we can somehow include this initial step and see if that changes the story. And of course, what would really be the better thing to do would be to actually ask yourself, how are genuine measurement devices, how are photon detectors really designed? They're in fact designed in very carefully engineered out of equilibrium states, such that a small perturbation will have a macroscopic effect. And then, of course, there are sort of more foundational questions or theoretical questions about how to include perhaps non-projective measurements, how do you do that kind of update, continuous variables, how can we look at paradoxes, all of these things. And with that, I'd like to thank our sponsors, and then, of course, the many collaborators that made this actually possible. These guys were involved in the equilibration stuff in the first part, and then in the measurement associated part, you'll see Felix is actually in the audience today, and some further collaborators, and then thank you very much.
I have clearly underestimated how ambitious your talk going to be, because not only you have solved the problem of irreversibility, but also quantum measurement.
Like I said, ambitious questions and partial answers.
Yes. Okay. So I'm overwhelmed. Okay. So we have time for questions now.
Please. Can you shout? I won't be able to hear very well.
This quantum measurement problem. So your statement of the problem is pretty peculiar to me.
So just to be clear, when I said I solved the measurement problem, I was absolutely joking. I was 100% joking. This is not the measurement problem. This is the question: when should a physical system? When do we decide to count a physical system as an observer or not? That's really the question I want to solve, which is not the same thing. Just to be clear. Sorry, I don't know if your question is.
So you introduced. So you assume that there are unity and non-unity processes.
Everything is unitary.
Yeah. So like the real measurement problem, I said it's not about measurement problem. Still, I want to ask that how do you answer that question?
What is the measurement problem? Yeah. No, what is the measurement problem? I'll state the problem and I'll see
it's a conflict between these two postulates. Like one is there is unity dynamics, and then suddenly we introduce collapse postulate, state of zero.
So the state update. So that's the question, as I said before. How do you get a single outcome? And as I told you before, I have a rule that I don't discuss that in a lecture room, but only in the pub with a beer in hand. So what are you doing tonight?
Okay. So then, more questions. Yes, please.
In the last couple of slides, you showed this broadcasting Hamiltonian, right? Can you go more general than that? Is it necessary to be this shape?
So it's a very interesting question, and it's a question that's not really restricted to looking at a measurement as an equilibration process, right? So any dynamical model of measurement that, as a first step, postulates some kind of Hamiltonian. Immediately, you have to start saying, okay, which Hamiltonian? What constitutes a measurement Hamiltonian? And so, if you want your system, if you want the probabilities associated with the measurement outcome at the initial moment in time to be preserved, then you need something like this part at the very least. You need this term because anything other than this will start connecting. Let's say if it's the 0-1 basis of some qubit, and if you don't have 0-0 and 1-1, but rather, let's say, a term that says 0-1, of course, some of your probability for having the one outcome will start being connected to the probability of having the zero outcome, and so your probabilities won't be preserved through the evolution. So, I mean, this point goes back all the way back to von Neumann's classic von Neumann Hamiltonian, where you say, if I want to measure a quantity A associated with some self-adjoint observable A, the appropriate interaction Hamiltonian to do that is A tensor B, where B generates or let's say agent A tensor P. Yeah.
Exactly, yes.
Yeah. Actually, I think it's X. But anyway, it doesn't matter. Where the second thing, acting on your sort of apparatus, your pointer system, your observer, whatever you want to call it, then generates some kind of translation, some evolution in your pointer observable on that system. So that aspect of it is necessary under that condition. You could then say, okay, well, maybe we don't want that condition, fine. Then one has to talk about timescales, how you're going to extract the information out such that the probabilities are encoded in the second system fast enough without somehow disturbing the probabilities so much that the outcome that you get, the probability distribution you copy into your pointer state is not somehow biased, not too distinct from the initial one you started with. That's a whole question in itself that people have discussed for nearly 100 years now. And then this sum form of this, that's really saying I don't want my Hamiltonians to interact with each other, right? My environmental fractions to interact with each other. Of course, that could be relaxed too, but then you have to be careful about exactly the way in which you relax that, so that you're not copying information from your system into one of your observer systems, if you like, while at the same time its interaction with some other observer system is washing that information away or rotating that vector, if you like. And again, so that has nothing to do with equilibration. These are purely statements about the dynamical modeling of measurements.
Okay, so more questions?
Please.
Well, maybe a follow-up, because it was super quick. You showed that the error equilibrates or saturates at the value which is gapped, and then only if n grows exactly. So now, given that the nice thing, n is the number of I.
Yes, sorry. So this is how many qubits are you gathering together into
so it's effectively how big is the first part of the Hamiltonian, right? Because it's the measurement.
So sorry, in this, you're right. I did just blast through this.
Yes.
So the example here is a qubit being measured.
Yes.
And the question is, if I take the systems that I'm coupling to, it's somehow the largeness of this that's inducing this action. That's the whole point of this kind of equilibration hypothesis. But what kind of largeness is important? Is it simply the high dimensionality of the system that you're coupling to, or does it matter that it's made of lots of small systems? So in this previous round, we showed that you get this exponential growth with the number of subsystems, but is that sort of necessary condition? Maybe it's necessary for the exponential nature, but is it physical?
So if you just say what is dk and what is m.
So this is the dimensionality of the system that you're coupling to. So you can pick a
Is the dimensionality of the apparatus?
Yes, exactly.
So, okay, so it's not enough to have a huge apparatus, you gotta have a many.
Under this model.
Sure.
And that comes from the fact that actually when you think about lots of systems which aren't interacting with each other and you randomize over the Hamiltonians that they have, you're doing far less randomization than if you consider one single system and then randomize over that.
Sure.
Okay, yes.
You showed those papers about cold atoms and some equilibration there.
Yeah.
And what are the scales of these effective dimensions there? Can you describe what happens?
That's a brilliant question. If you can solve it, then let me know.
Okay.
So I mean, if you have the Gross-Pitayevsky equation for a Bose-Einstein condensate, this is only solvable in very, very limited cases. And it's not, and it's solvable in the sense of you can kind of solve for the broad scale evolution of very particular observables. It's not the case that you can simply write down a matrix, which is the Hamiltonian, diagonalize that and get the spectral decomposition of it, and then plug that into the formula for the effective dimension. I mean, it'd be wonderful if we could do that. But we need to find a workaround for that. Either we need to find a very simple model. If we want to make this connection with cold atoms, we either need to find very simple models where you can do that. And there is some hope for that. There's a Luttinger liquid approximation for a certain context in one of these experiments, which can be mapped to a spin chain. And my hope, since I haven't really looked into this enough yet, my hope is that then we can kind of solve the spin chain model and then use that to say something about the Luttinger liquid. But I said that to an experimentalist friend who actually has a PEC in the lab that can be approximated by the Luttinger liquid model, and he went, and that was it. So. Judging just from his facial expression, I guess this is going to be hard. Or the other way around, which is really what we should do as theorists. It's our job to describe experiments. It's not experimentalists' job to cook up something very strange and very exotic that just about somehow manages to squeeze itself into our theory, right? So the more sort of intellectually honest approach would be to take what we have founded in this quantum information tradition where we get to say, here's your Hilbert space, and here's your Hamiltonian, and this is the dimensionality and all these things, and say, okay, no, these are the things that people can really do. This is how they're able to model them so far, and how can we model them in a better way such that the physical principles that we're trying to illustrate here can be incorporated into that model. that's the better way to do things. It's very easy for me to say that grandiosely in front of an audience right now, but the technicality of doing that, of course, is very difficult. And that's why, I show you a nice Hilbert space, a nice Hamiltonian, and write things like the dimensionality of the Hilbert space.
Okay, so maybe some last question on some fundamental things.
Yeah, I would have one. So I missed somehow how the past hypothesis, how did it enter the bounds that you got, this low entropy starting state?
So in the simulation that we did, you can see this fairly. Sorry, 1 second. So we started with this initial state here, which is has entropy 0 with respect to for any entropy defined with respect, or any reasonable entropy defined with respect to the bulk magnetization, because it has a definite value of the bulk magnetization. All of the spins are pointing down, has the lowest possible value, and there's only one state associated with it as a 1-to-1. There are only 2 cases where the bulk magnetization as an observable is 1-to-1 states and outcomes, and that's all the spins pointing down and all the spins pointing up. Everything else, there's some kind of combinatorics that allow you to have multiple.
But I rather meant, how did it enter into those fluctuation results of yours?
It didn't.
It didn't. Okay.
Yeah. The proof is that the entropies converge to their equilibrium value. Proving that their equilibrium value is higher than their initial value is impossible. Because
Got it.
I can cherry pick an example where I will have some much higher. Much is actually, I've never managed to find much higher. That's the strange thing about this, is a priori no, but every time you try to do it in practice, it happens. So it's kind of tantalizing. I'd say every with an asterisk. You can, if you want to cherry pick a value or a situation where the initial entropy is higher than its equilibrium value, you can do it, but in my experience, only by a little, and only really within the limits of like some sort of early fluctuations. I've never seen something like this graph. Okay, this is the observable, but you get the point. I've never seen something like this graph, but the inverse.
Yes.
Okay, just about this side, I have a question, because it seems that timescales at which you equilibrate, they are sort of the same for different sizes of the system. So this formalism of temporal typicality, like to what extent it addresses the question of timescales of equilibration? So can you derive some bounds? What is I was looking at many years ago on those.
It's a brilliant question and a tough one. So there's a naive, or if you like, an initial statement that one can make about this, in the sense that you can say, okay, well this gives you the time scale, right? There's a t in there, but this equilibration happens very quickly. It doesn't happen with 1/t. It tends to happen. It depends on the circumstance you're talking about. Of course, if you have a one-dimensional chain, you have sort of Lieb-Robinson behavior, for example, where there should be some time some notable time before the last. If I open a can of something very smelly here, it's going to be a little while before you smell it, right? Equilibration shouldn't happen incredibly quickly, and we should all be very happy for that, of course, because it means that the universe hasn't suffered heat death yet. But in a very small system, the equilibration tends to happen very quickly. In fact, connecting the 2 parts, if one can really describe the measurement process as an equilibration process, in those contexts it should happen incredibly quickly. We measure the collapse as an instantaneous thing. We know that it's instantaneous, and there are various very interesting works showing what the real timescale of collapses tend to be, but it's very fast. And so more work needs to be done. Somebody in the audience mentioned the Gogol and Isert work. So one of the things they did that was quite nice was to discuss equilibration times. There's also a paper by Thiago de Oliveira in Brazil, making some good, very general arguments, but quite hand-wavy about why systems under most conditions should equilibrate quickly. But I haven't really answered your question. I've talked around that, as you can see.
Right, but when I look at this formula, so that t should be such that the bound is small. This is what you mean by
yes. So
so it's like
any
proportional to r over d effective.
Yeah, it's 1/t. It's it's an inverse linear scaling with t, which is not good enough to describe something like the experiments that I described before. These are incredibly quickly equilibrating. This is not.
Okay, because the effective is relatively small. It's not like exponentially large.
It doesn't have any time. It doesn't have any temporal. Just gives you the coefficient. But the problem with trying to be as general as possible is that you end up being as vague as possible, right? And so without any additional assumption, if I had shown you a bound that had some kind of exponential equilibration time, exponentially fast equilibration, you should absolutely doubt me because I didn't make any physical assumptions that should give an exponential scaling time. In fact, if I have a chain, the Lee Robinson example, if this chain is very, very, very long, then it should take a very long time if I start in sort of in equilibrium mostly around here, and then do some kind of perturbation here, it should be a very long time.
Sure, so it's like natural to have those bounds in terms of locality of your interaction size of the system, etc.
Exactly. This is how the people who've worked on equilibration time and shown fast equilibration times, these are precisely the assumptions that then need to be made in order to.
Okay, I think we should conclude. So let's thank the speaker again.